Welcome back. Now, we will study reversibility of Markov processes or reversibility of CTMCs. All right. Recall that for a DTMC in steady state, that is if you start off DTMC in pi I, then pi j star, which is basically pi j over pi I p I j is the reverse transition probability. This we studied in great detail. So, just to refresh your memory, we said that for a DTMC, the reverse, if you have a DTMC running in forward time, the reverse time is always a Markov chain, but it could be a inhomogeneous Markov chain. However, if you run the forward Markov chain in steady state, that is you start in pi I or you let the Markov chain run for a very long time, so that it reaches pi I. So, either way, if the forward running chain is in steady state, the reverse chain is also a homogeneous Markov chain. Okay. It is a homogeneous Markov chain with transition probability p I j star given by this expression on your screen. Now, we are going to assume that the embedded DTMC is in steady state. Okay. Embedded DTMC has transition probabilities p I j. So, the reverse embedded is the reverse process of the embedded DTMC will have reverse transition probabilities p I j star, right. But in the CTMC world, you are also having these holding times, right. So, just to show you a picture, what happens is let us not put 0, because let us say it is assuming in assume that we are in steady state. So, here are all the state transitions. So, in all this, so there are transitions in the forward time. So, these are governed by p I j's. In the reverse time, these transitions are governed by p I j star. All right. The transition probabilities between the states at the transition instances. So, let us say you are in some state j. All right. So, if you look at these little delta intervals, so the holding time in each of these intervals between successive transitions is exponential with parameter nu j, given that you are in state j, right. So, the transition probability, right. So, the probability that you leave state j from this slot to this slot will be what will be nu j delta plus little o delta, right, in forward time. So, even in reverse time it is true, right. The probability of going from, so it is after all an exponential random variable, the probability of going making a transition out of j in reverse time is also nu j delta plus little o delta, right. So, what happens is that when you look at it in forward time, you have these p I j transition probabilities and exponential holding times of rate nu j's whenever you are in state j. When time is running in reverse, you have p I j star transition probabilities with the same holding times, exponential holding times, right. So, the reverse process is also a Markov process, because you have it, but the embedded Markov chain is different, that is all that we are saying, right. So, when the Markov process runs in forward direction, the embedded transition probabilities are p I j and the holding times are exponential nu j whenever you are in state j. In reverse time, the embedded DTMC has transition probabilities p I j star, which is given on your screen, and holding times continue to be the nu j's corresponding to those states, all right. And of course, just like in the discrete world, the p j, which is pi j over nu j divided by sum over k pi k over nu k, will remain the same for the forward process as well as the reverse process, right. Now, what about the reverse rates, right? If you look at q I j star, right, which is the rate of transitions from I to j in the reverse process. this is just Pij star times nu j, sorry nu I, right, because you are going from I to j, Pij star times nu I, right. You are holding for I nu I duration and then jumping to some state j, right. So, if you write this out, Pij star we know to be equal to, from the earlier discussion, Pij star we know to be equal to that. So, if you just put that expression into this, you get pi j over pi I think I made a mistake, p j, this should be p j I, sorry, I apologize. So, this should be p j I, yeah, p j I nu I, all right. So, these are your transition probabilities, transition rates in the reverse process. Okay. So, it is pi j over pi I, let me just check that this is correct, it is nu j, so it is sorry nu I pi j p j I over pi I, all right. So, this I can write this again as, if you just look at this as pi j over pi I am just going to rewrite this q j I over nu j times nu I. So, what have I done now? I have just replaced p j I with q j I over nu j, right. This is just very basic algebra, right. So, what does this work out to be, right? This is just pi j over nu j divided by pi I over nu I, correct, times q I j. So, and what is pi j over nu j divided by pi I over nu I is just p j over p I, right, because we know that p j is proportional to pi j over nu j, that we already know, right. So, what does this imply? After these manipulations you get q I j star is equal to p j over p I q I j. Sorry, q j I. So, I again got this. So, this again I made a mistake here, I apologize. So, this is q j I, right. So, I made a mistake. So, yeah, this should be q j I. I made the same mistake twice, apologies. Yeah, now this is correct. Okay. So, now this is nice, p I q I j star is equal to p j q j I. Okay. So, q j I star, which represents the reverse transition rates, is given by q I j star is equal to p j over p I q j I. Okay. So, what are we saying? So, if you are given a forward CTMC with transition rates q I j, which completely specify the process, and assuming that this is a nice CTMC with the steady state P I and all that, the reverse CTMC, the reverse process is in fact a CTMC whose transition rates are q I j star is equal to p j over p I q j I, all right. Now, definition, now we come to the important definition of reversibility of a CTMC. So, just like in the DTMC world, so remember that if a forward steady state DTMC is a forward thing is a Markov chain, the reverse chain is also a Markov chain with transition probabilities p I j star, but that is not what reversibility is. The reversibility means that the reverse Markov chain and the forward Markov chain have the same transition probability matrix, right. So, in the same spirit we will define CTMC to be reversible CTMC with steady state probabilities P j is reversible if q I j star is equal to q I j for all I j in S, okay. I.e. P I q I j is equal to P j q j I for all I j, okay. So, this is a definition. You say that a CTMC is reversible if the forward transition rates and the reverse transition rates q I j star and P is equal to q I j for every I j, okay. So, between any true pair of states, the transition rates in the forward process and the transition rates in the reverse process must be equal, which leads to the nice equation, this local balance kind of an equation, P I q I j is equal to P j q j I, okay. So, you can view this as some kind of a local balance in the CTMC world, okay. If this is the case, then the process is reversible, this definition, all right. Now, we can prove a lemma now that says that if the steady state probabilities P j's exist in an irreducible CTMC and sum over P I nu I is finite, then the CTMC is reversible if and only if the embedded chain is reversible. Embedded DTMC is reversible, okay. So, here we are saying that there is an equivalence between the reversibility of the CTMC and the reversibility of the embedded DTMC, okay. Reversibility of one implies the other, okay, both directions. Of course, assuming that this is a nice irreducible CTMC with sum over P I nu I less than infinity, right. You do not have this crazy irregular avalanche process and all that, okay. So, this is very easy to prove actually, if you just look at it, if so assume the CTMC is reversible, all right, then what do you get? P I q I j is equal to P j q j I, right, which means that P I q j I is what? P I j times P I j q I j is P I j times nu I and q j I is P j I times nu j, right. So, you have this. Now, we know that, so P I nu I in the world when sum over P I nu I is finite, this if you take that term P I, take that term, right, that is something that is proportional to pi I, right, and likewise the corresponding term here is proportional to pi j. So, you get pi I P I j is equal to pi j P j I, right. This implies that, and of course, each of these pi i's is positive, right, because sum over P I nu I is finite. This implies that embedded DTMC is reversible, okay. So, one direction is shown, if the CTMC is reversible, then the embedded DTMC is reversible. The converse is is similar. Okay. So, this lemma very simply characterizes the reversibility of the CTMC as being equivalent to the reversibility of the embedded DTMC, and since we understand DTMC reversibility well, so there is not so much of a conceptual difference between reversibility of CTMC and reversibility of the embedded DTMC. They are in fact exactly equivalent. Now, just like in the DTMC world, see there was this desirable feature. Of course, if you have pi I Pij is equal to pi j Pji for the steady state probabilities pi i's, then you know that the DTMC is reversible, but you know sometimes you may not know the steady state probabilities pi j's, right. So, in that case we had a theorem that said if you manage to find any numbers at all by guesswork or whatever that satisfies these local balance equations, then you immediately could assert that these pi j's are in fact the steady state probabilities, and that the Markov chain is reversible, and that the Markov chain is positive recurrent, right. A similar result holds in the CTMC case. Okay. So, even if you do not know the PI's, right, you may not know the steady state probabilities PI's for a CTMC, but if you do manage to find some numbers PI that satisfy Pi Qi j is equal to Pj Qj I, then you can prove that the CTMC is reversible. Okay, this is a important theorem. For an irreducible CTMC, assume that Pi is a set of non-negative numbers summing to 1 such that sum over Pi nu I is finite and Pi Qi j is equal to Pj Qj I for all I j in S. Then one Pi is the set of steady state probabilities for the CTMC. Number 2, the process is reversible, maybe say the CTMC is reversible, and the embedded DTMC is positive recurrent. Okay, so, this is a very nice theorem. So, if you manage to find somehow guess some numbers Pi, you do not know the steady state probabilities, right. So, you somehow manage to find the numbers which satisfy local balance and such that sum over Pi Q nu I is less than infinity and Pi sum to 1, then the Pi's that you did guess are in fact the steady state probabilities and reversibility comes for free and the embedded DTMC is positive recurrent. All right. The reason that this is true is if you just look at you sum this local balance equation. If you have sum over I Pi Qi j is equal to sum over I Pj Qj I, right. So, Pj comes out of the summation and sum over Qj I is what? Is just nu I, right. sorry, this P nu I, Pj nu I, this is Pj outside, Pj nu I, correct. Sorry, I got this wrong, Pj nu j, right. So, this all I am saying is this Pj comes out, sum over Qji is nu j, right. So, I have sum over I Pi Qij is equal to Pj nu j. Now, these are in fact the balance equations that Pi satisfy, right, and of course, sum over Pi is equal to 1, that you already know, right. So, this implies Pi's are all positive and are in fact the unique steady state probabilities of the CTMC, which we already saw, right. This we already know. If you find a solution to Pi which satisfies the balance equation sum over Pi Qij is equal to Pj nu I, then those Pi's are in fact the unique solutions of the steady state probabilities of the CTMC, right. Now, Pi's are in fact the steady state probabilities of the CTMC and they satisfy local balance, right. Therefore, they must be reversible, the CTMC must be reversible, right. Once you know now that Pi's are the steady state probabilities of the CTMC and you know that local balance is satisfied, therefore, the CTMC is reversible. Okay. And now, since sum over Pi nu I is less than infinity, you can also get your pi i's to be something strictly positive, right, meaning that the embedded DTMC is positive recurrent. Okay. So, those steps you can complete, but this is a very useful result, this is a very nice result to have. Finally, there is a extension of this theorem which says that if you somehow manage to guess numbers Qij star, all right, which satisfy certain properties, then you automatically get the transition rates of the reverse process. This is like a generalization of the theorem that we just saw. For an irreducible CTMC, with transition rates Qij, suppose that a set of positive numbers Pi satisfy normalization sum over Pi nu I finite full stop. Also assume that a set of non-negative numbers Qij star satisfy the equations for all I Pi Qij is equal to Pj Qji star for all I comma j. Suppose this Qij star satisfy sum over Qij is equal to sum over Qij star for all I, and P I Q I j is equal to P j Q j I star. Okay. Then 1 P I is the set of steady state probabilities of the CTMC. Number 2, the embedded DTMC is positive recurrent. And 3, perhaps most important of all, Qij star, whatever you guessed, this Qij star are in fact these transition rates of the backward CTMC. So, you have a CTMC running in forward time, all right, with the rates given by Qij, okay, and somehow you manage to guess some numbers Pi and some numbers Qij star. You do not know anything about these numbers except that Pi is sum to 1, sum over Pi nu I is finite. Also this Qij star satisfy the two equations so shown here. Okay. Then Pi's are in fact your steady state probabilities. The embedded DTMC is positive recurrent and the Qij stars that you manage to find satisfying these equations are in fact the transition rates of the backward CTMC, all right. Please keep in mind that we are not saying that this CTMC is reversible, no, right. We are just saying that Qij star I managed to find that satisfies this property, then that Qij star is in fact the transition rates of the backward Markov chain. Okay. So, how do we prove this? If you just look at P I Q I j is equal to P j Q j I star for all I, right. Now, you can just sum this, summing over I, right, you get sum over I P I Q I j is equal to sum over I, sorry, P j Q j I star, is not it? J make a P j Q j I star. So, this is a j, all right. Sum over I P j Q j I star, all right. That is equal to P j comes out sum over Q j I star. Now, sum over Q j I star is equal to sum over Q I j, right. Now, what is sum over Q I j? Nu j, right. So, this is equal to P j sum over Q j I by assumption, that is equal to P j nu j, all right. So, sum over P I Q I j is equal to P j nu j. So, these are again the balance equation, right. So, Pi's, so here are so the Pi's that I managed to guess satisfies the global balance equations, sum over P I Q I j equals P j nu j, right, for all I. So, this implies, and of course, Pi's are all positive and they sum to 1, this implies Pi's are the unique steady state probabilities, right. They are the unique solution to this equation and they are the steady state probabilities of the CTMC. Okay. Now, these Pi's are all strictly positive and sum over Pi nu I is finite. So, I can get strictly positive pi i's from this, from these Pi's, which implies that the embedded DTMC is positive recurrent. And finally, now that Pi's are the interpretation of the steady state probabilities, then Qij star which satisfies which satisfies. So, you have Qj I star is equal to P I Q I j over P j, right, must be the reverse transition rates, backward transition rates, because that is, but that we know to be the backward transition rates, right. If you want, you can replace P I by you know that pi i's are positive. So, you can write this in terms of pi i's and nu i's, and then argue that these are in fact the backward transition rates, as we have already done. This is very useful if in guessing somehow that the behavior of the reverse process. Okay. This can be used in for example, a Jackson networks of queues. Okay. A Jackson network of queues is a connected queuing system, which we will briefly study later, but this kind of these two theorems, which are known as guesswork theorems, right, are useful in many contexts. Whenever some educated guess tells you something about either the reversibility of the process in the first theorem, or in the second theorem it does not say the process is reversible, it just characterizes the reverse transition rates. All right, we can stop here for now.